All right, good morning, afternoon, whatever time it is that you happen to be viewing this video. We're going to go ahead and get started into the information from Chapter 5 in our text on gases. Now, we started talking about this a little bit last week in class, as we were finishing up the quarter, but now we're going to actually take some time to delve into it a little bit and maybe put some commentary to the PowerPoint that you've been looking through. Now, our learning goals for the first section are going to be, I'll be able to describe the interactions between gases, based on the postulates of the kinetic molecular theory, or KMT, and I'll be able to convert between different units of pressure. We spent some time on the units of pressure. I just wanted to do a quick recap of that, and then we'll get into the kinetic molecular theory a little bit more. Now, why in the world do we want to study gases in the first place? Well, there are a lot of things that actually act on us and that we interact with on the regular basis that involve gases and how they behave. And this helps us to understand a little bit of how science works per se. Now, some of the basic properties we know of a gas. One, if I were to take any container, no matter what the shape, no matter what the size, if I was to fill it with a gas, or just even take it and then try to cover it, the gas that's trapped inside is going to fill that container. No matter how much gas is there, it's all automatically going to try to fill that container. It's going to bump around and it's going to get as far away as it can and move away around as much as it can. Now, because of this, that's going to leave a lot of space between the molecules, which means it can be compressed down. It's going to mix easily with other gases, as expressed by the fact that we're breathing in nitrogen and carbon dioxide and oxygen and argon and all these different things at the same time, and it exerts pressure on its surroundings. So no matter what the size of the surroundings, the size of this room that I'm in, there is pressure being exerted on the walls, on the windows, on me, on the chair, on everything that's around. Now, pressure overall, if we look at it from a physics standpoint, is looking at the amount of force applied per unit area. The unit that we usually look at is what we call a Pascal. This is the SI unit. It's a Newton over meter squared. Now, when we deal with one standard atmosphere, we're looking at 101,325 pascals, or as we talked about before, 101.3 kilopascals. Now, here are a couple other equivalences or equalities, that you'll be using throughout. That 101.3 kilopascals is equal to 1 atmosphere, which is also equal to 760 millimeters mercury, or 760 torr. And we'll get to those just now. Now, many times what was used in the past to actually differentiate or to find out what the pressure was is what's called a barometer. Now, this barometer, the old school barometer, was a container filled with mercury with a tube in there. Now, this had a little bit of a vacuum, so they set it up so that there was no other air inside of the container. And what this does is, as the gas pressure hits the surface of the mercury, here, all over, it pushes some of the mercury up the tube. Depending on how far it went, that will tell you what the atmospheric pressure was. So they found that commonly it was 760 millimeters of mercury. That's where we get that unit from. 760 millimeters up into the tube. Now, the other way that we can also look at this is what we call a manometer. Now, we are used to this type that the lady's using in the picture. We're used to being able to go and check the tire pressure in our car and the little thing pops right out. But what they actually used to do is they had a container that looked a little bit more like this. It looked like a bulb. I apologize for my bad drawing. And it had a tube that came off of it. I apologize again. Now, with this tube being the size that it was, there was mercury that was here. So it wasn't a lid here. There was mercury that was put in. And depending on how far the mercury went, would tell you how much pressure the gas in here was exerting. So they would measure this distance, and if this distance was, say, 350 millimeters, then you knew the pressure of the gas had to do with 350 millimeters. Okay, now let's go ahead and get rid of my horrible drawing. Next time I'll just try to find a picture. It's okay. We'll keep moving. Now, here's a classic experiment that we actually do called the collapsing can. We want to look and see what actually happened to go from this full can, as you can see there's some steam coming out of, to all of a sudden it being crushed. What's the difference between the picture? Now, oops, let me go back. Now, one of the things that I'll point your attention to is look here at the bottom of the screen. You notice that here it's being heated. So it's being heated, the water that's inside is being turned to steam. Now, as we continue to look, now we note that, hey, we have a cap on this thing, and the heat is gone. So what do you think caused it to crush in between? Before it was being heated, no cap. Now there's a cap on it, there's no heat, and all of a sudden it crushes down. We're going to look at the relationships between our gas particles, and I believe that should help us to understand why the can crushed the way that it did. Now, here's an example for the pressure conversions. If we're given the pressure of a gas measured in 2.5 atmospheres and asked to translate it or put it into torr and pascals, how would we go about doing that? Well, starting to look very much like it did when we dealt with our moles. Notice that we have 2.5 atmospheres times, we brought our 1 atmosphere down to the bottom and 760 torr at the top. Why do we set our conversion factor up like this? Because our goal is we want to be able to cancel out this unit atmospheres. The way to do that, put it at the bottom of our conversion factor and multiplying 2.5 times 760. Now, how would we go about doing the same thing for our pascals? Well, what was our unit? We said that 1 atmosphere was equal to 101,325 pascals. So, end up multiplying the same way. We have our 1 atmosphere, cross out, atmosphere cross out, multiply 2.5 times 101,325 pascals to get our final answer. Now, this part is not very crazy or difficult. Please let me know if you're running into any issues and I will do my best to try to assist you. Now, from there we move into our kinetic molecular theory. And this is basically looking at how the gas particles themselves, how they move, how they interact in an ideal situation. Now, the first postulate that we look at and that we sort of get to assume when we're dealing with gases is that the particles are so small that compared to the distances between them and all those different things that it's basically negligible. So we assume that all of the gases that we work with have the same mass and are the same size. This makes it a lot easier for us because we're not so concerned with a lot of the other intermolecular forces and different things that come in. So we assume at the beginning for the kinetic molecular theory, all the particles are exactly the same. Okay? Now, the second is that the particles are always in motion. So there's never a point where they stop moving or slow down. It's that they're going to be colliding with the walls, with each other, all those types of things. The third postulate or assumption is the particles are assumed to exert no force on each other. So remember how we talked about intermolecular forces before, our dipole-dipole and London dispersion and hydrogen bonding. In the situation where we're dealing with our gases, we assume that none of those actually have any effect. So there's no attraction between the molecules, there's no repulsion between the molecules. And last but not least, that the average kinetic energy of the collection of gases is assumed to be directly proportional to the temperature in Kelvin. So if it says that it is 325 Kelvin, we assume that that is also going to tell us how fast the molecules are moving within that system. We don't try to assume anything else. We don't try to take into account anything else. If the temperature says it's this, we're saying that that's what is the direct proportion or direct relationship of how fast those molecules within that system are actually moving. Now, this is going to allow us to understand a little bit more about the velocity at which these particles are moving in the system. Now, let's take a little bit of a look and do a check, I guess you'd say. Now, you're holding two balloons, same volume, one contains helium, one contains hydrogen. Complete the following statements with different or the same and be prepared to justify your answer. So, look at the sizes of the balloons, and we're going to go from there. Now, the pressures of the balloons, according to what you're seeing here, would be where? What would you state them as? Well, considering they're the same size, we're going to actually say this one is the same. Okay? Now, what about the temperatures? Well, if we understand what we just talked about for our kinetic molecular theory, if they're the same pressure, they have the same pressure, and they're the same size, most likely that means that they are the same temperature. Oops, that's not supposed to be temp, that's supposed to be same. Sorry about that, guys. All right, now, what about the number of moles? Well, we're going to actually get to this part in just a second, but thinking about what our good friend Avogadro, one of the things that he's going to point out is if we have the same temperature, same pressure, and the balloons are the same size, the molar relationship should also be the same. And last but not least, the densities of the gases are going to be what? Well, considering we have two different gases with two different masses, they're actually going to be different. Now, this leads us to our last little bit where I was talking about the velocity of those molecules. There's a way for us to actually determine the velocity of a molecule, of the molecules within gases, based on these factors. We have our gas constant, which you notice that now we have switched our units. So we have 8.3145 joules per kilogram times mole, or times Kelvin, sorry. We have the temperature in Kelvin and the mass of the mole in kilograms. So we change the units, and with changing the units, we change the value here. And for our mass, we're now dealing in kilograms. That's going to be very important as we get ready to plug it in. Now, this formula will also be given to you on your reference sheet, so you don't have to memorize it, but just memorize how to use it. And I'm gonna post a tutorial on how to use this this formula a little bit later. Now, this is where we're gonna end our first video. It's been great talking with you about it, but now we got to go and actually put it into practice. So please let me know if you have any questions. Send me an email, send me a message, write a comment down below, and we'll do the best that we can to make sure you understand and are ready to complete the material. Have a good day, and I'll talk to you later.